Hello dear students, this is Vishal sir from Ikra High School. Today we are concluding part 2 for chapter 10 Light, Reflection and Refraction from standard 10 NCERT syllabus. The topic would be sign convention for reflection by spherical mirror. But before we start the topic, let's understand a graph. As you can see on the screen, there are two lines, a vertical y-axis and a horizontal x-axis. They both meet perpendicularly at a point called origin. As you go upward on the y-axis, you will find on going upward all the numbers are becoming larger with positive digits. As you go downwards, the same is in opposite way. The number minimizes to negative. As you go on the left hand side, that is on the x-axis, you will get all negative numbers with minimizing range. And as you go on the right hand side, you will find all numbers are positive with larger numbers. So this is a concept of graph, and the same will be understood in our mirror formula. The new Cartesian sign of convention is taken as the pole being the origin and the principal axis is taken as the x-axis. The conventions are as follows. The object is always placed to the left of the mirror. This implies that the light from the object falls on the mirror from left hand side. So if you see in this diagram, this is the new Cartesian sign convention for spherical mirror. Now, the light will be incident from the left hand side to the mirror. So the direction of the incident light would be like this. The object will be on the left hand side. So the distance from the pole towards the object will be negative. In the same manner, the distance from pole to the image will be negative, implies for the height. If the object is standing erect, it would show positive sign, and if it is inverted, it would show negative sign. If the image is formed behind the mirror, it means it is on the right hand side of the pole. That means the distance will be positive. So x dash x is the horizontal line, that is the principal axis, p is the origin, and mn is the perpendicular line. All distance parallel to the principal axis are measured from the pole of the mirror. All the distance measured to the right of the origin are taken as positive, while those measured to the left of the origin are taken as negative. Distance measured perpendicular to and above the principal axis are taken as positive. Distance measured perpendicular to and below the principal axis are taken as negative. Now let's go for mirror formula. When you want to study about the mirror formula, you have to keep in mind the new Cartesian sign convention for spherical mirror. In a spherical mirror, the distance of the object from its pole is called the object distance. The distance of the image from the pole of the mirror is called image distance. You already know that the distance of the principal focus from the pole is called focal length. So here, three terms are considered for forming a mirror formula: object distance, image distance, and focal length. When any equation shows a relation between these three things, it is called mirror formula. It will be written like this: 1 upon v plus 1 upon u is equal to 1 upon f. This formula is valid in all the situations for the spherical mirror for all the positions of the object. Magnification. Magnification produced by spherical mirror gives the relative extent with the image of an object is magnified with respect to the object size. So it gives a relative extent, how much is the image larger or smaller than the object. That is called magnification. It is usually represented by letter m, and it is the ratio of the height of the image to the height of the object. So if you know the height of the image and the height of the object, and if you find the ratio of both, you will get magnification. It is written as h dash upon h, where h dash is the height of the image and h is the height of the object. It can also be related to the object distance and image distance. So if you know the distance of image with the distance of object, then also you can find magnification. Some points that you have to keep in mind is the height of the object is taken as positive if the object usually placed about the principal axis. So normally the object stands in front of the mirror and it is erect, therefore its height is always positive. The height of the image should be taken as positive for virtual image, and if the images are virtual, it will be naturally erect. At that time also the height of the image will be taken as positive. But for real image, the height is taken as negative. Whenever you get a negative sign, it shows that the image is real. And when the height is or the value is positive, you can say the image is virtual. Refraction of light. Now, as you have studied earlier, reflection of light is the returning of light. Refraction of light is the bending of light. You must have seen some examples like this. Here you can see a pencil immersed in water. The pencil which is above the water seems straight, while the one that is immersed in water seems straight but different from the original position. It should be totally straight, but it seems bent. The point of difference or the media is the edge of the water. From the edge you can see a pencil immersed in water, and from the edge you can see a pencil outside the water. Pencil outside the water is in media air, a rarer medium, while the pencil inside the water is a denser medium, water. So light passes through two different medias, and while passing through two different medias, it takes a bend because the velocity of light changes while it crosses two medias. Light seems to travel along straight line path in a transparent medium. What happens when light enters from one transparent medium to another? Let's see the example. Have you seen the pencil partly immersed in water in a glass tumbler? It appears to be displaced at an interference of air and water. Let us consider the case of the apparent displacement of a pencil partly immersed in water. The light reaching you from the portion of the pencil inside water seems to come from a different direction compared to the part above water. This makes the pencil appear to be displaced at the interference. For the similar reasons, the latter appears to be raised when seen through a glass slab placed over it. These observations indicate that light does not travel in the same direction in all the media. It appears that when traveling obliquely from one medium to another, the direction of propagation of the light in the second medium changes. This phenomenon is known as refraction of light. Now what happens when the light travels from a rectangular glass slab? Let's go through an experiment. Here you can see a glass slab, and the incident light from the left hand side enters the glass slab. As you see, there is a slight band of the light in the glass slab. Again, when it emerges out of the glass slab, it has taken a bend. Here you can see the diagram more systematically with n dash as the normal, m dash as the normal. O is the incident ray, O dash is the refracted ray, and O dash H is the emergent ray. This emergent ray is parallel to the dotted line over here. The light rays has changed direction at point O and O dash. Both the points O and O dash lie on the surface separating two transparent media, where you have to draw perpendicular n dash to AB and m dash to CD. The light ray at point O has entered from a rarer medium to denser medium, that is from air to glass. The light ray has bent towards the normal. At O dash, the light ray has entered from glass to air, that is from denser medium to rarer medium. The light ray here has bent away from the normal. The ray EO is obliquely incident on surface AB, so it is called incident ray. OO dash is the refracted ray, and O dash H is the emergent. You may observe that the emergent ray is parallel to the direction of the incident ray. Why does it happen? The extent of bending of the ray of light at the opposite parallel faces AB, air glass interference, and CD, glass air interference, of the rectangular glass slab is equal and opposite. This is why ray emerges parallel to the incident ray. So refraction is due to the change in the speed of light as it enters from one transparent medium to another. This gives the following two laws. Laws of refraction of light. Number 1, the incident ray, the refracted ray, and the normal to the interference are two transparent media at the point of incidence all lie in the same plane. And number 2, the sine of angle of incidence to the sine of angle of refraction is constant, and that is constant for the light of the given color and for the given pair of media. This law was given by Snell, and that is why this law is called Snell's law of refraction. If I is the angle of incidence and R is the angle of refraction, then sine I upon sine R is equal to constant. This constant value is called refractive index of the second medium with respect to the first, the refractive index. The absolute refractive index of a medium is the ratio of the speed of light in air or vacuum to the speed of light in that medium. So when you take the ratio of the speed of light in vacuum and the speed of light in any of the medium, you will get a value, and that will be called the refractive index of that medium. Let's study the refractive index from textbook. You have already studied that a ray of light that travels obliquely from one transparent medium to another will change its direction in the second medium. The extent of the change in direction that takes place in a given pair of media may be expressed in the terms of the refractive index, the constant, appearing on the right hand side of the equation. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. It turns out that light propagates with different speed in different media. Light travels fastest in the vacuum with speed of 3 into 10 raised to 8 meter per second. In air, the speed of the light is only marginally less compared to that in vacuum. It reduces considerably in glass or water. The value of the refractive index for a given pair of media depends upon the speed of light in two media as given below. Consider a ray of light traveling from medium 1 into medium 2. So let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. So if you want the refractive index of medium 2 with respect to medium 1, you have to keep the equation like this: speed of light in medium 1 upon medium 2, and that will be considered as a refractive index of medium 2. But if you want the refractive index of medium 1 with respect to medium 2, then you have to write the speed of light in medium 2 upon the speed of light in medium 1. If medium 1 is vacuum or air, the refractive index of medium 2 is considered with respect to vacuum, and this is called the absolute refractive index of the medium. It is simply represented as N2, and C is the speed of light in air and V is the speed of light in medium. Then the refractive index of the medium is Nm, given by Nm is equal to speed of light in air upon speed of light in medium. So you have to write like this, and the absolute refractive index is simply called refractive index. Our next topic is refraction by spherical lens. Now these are lenses. They are transparent, and so the light passes through it on the other hand side. Earlier we learned about mirrors through which the light doesn't pass but it reflects back. Here the light passes on the other hand side. The differences that you are going to consider in lens is, instead of pole in mirror, here you will have optical center. Focal length would be there, but there will be two focus. The second focus 2f2 is the center of curvature, but we are not considering center of curvature, or we are not regarding center of curvature in lenses. Instead of it, we will consider it as twice the focus. Then on the other hand side, you will have another focus f2 and 2f2. This A diagram you see on the chart is a convex lens. It is a double convex lens. Let's study spherical lenses and its refraction. So these are two lenses. In lenses that are different from mirror, mirror reflects the light, while lenses converge or diverge the light on the other hand side. Here you can see two lenses, lens A and B. The first one is a double convex lens. The second one is a double concave lens. Here, instead of pole, the center would be considered as optical center. The focus would be on both hand side. In convex mirror, you will have a real focus. All the parallel rays to the principal axis will converge to that focus. So this will be called converging lens. Instead of center of curvature, we would be considering the point as twice focus. On the left hand side, you will consider it as 2f1 and f1, and on the right hand side where the rays converge and meet at a real focus, it will be called f2 and 2f. But in a concave lens, you will have diverging lens. They don't tend to meet at focus, but we assume that they meet at a focus, and that's why this will be a virtual image. Now the terms related to lens. A lens, either a convex or concave, has two spherical surfaces. Each of these surfaces forms a part of the sphere. The center of these spheres are called center of curvature of the lens. The center of the curvature of the lens is usually represented by letter C. Since there are two center of curvature, we may represent as C1 and C2. Imaginary straight line passing through two centers of curvature of a lens is called principal axis. The central point of the lens is its optical center. It is usually represented by letter O. A ray of light through the optical center of the lens passes without suffering any deviation. The effective diameter of the circular outline of the spherical lens is called its aperture. Such lenses are called thin lens with small apertures. Now let's see through an example the different terms associated with lens. Here you can see a convex lens converges the rays of the sun at a point, and that point burns the paper. So let's read the example thoroughly in the textbook. The paper begins to burn, producing smoke. It may even catch fire after a while. Why does this happen? The light from the sun constitute parallel rays of the light. Here you can see these are the parallel rays of the sun. These rays are converged by lens at the sharp bright spot formed on the paper. In fact, the bright spot you got on the paper is the real image of the sun. The concentration of the sunlight at a point generates heat. This causes the paper to burn. If you pass parallel rays from the opposite surface of the lens, you will get another principal focus on the opposite side. Letter F is usually used to represent principal focus. However, a lens has two principal foci. They are represented by f1 and f2. The distance of the principal focus from the optical center of the lens is called focal length. The letter F is used to represent focal length. Image formation by lenses. Now you can see four different diagrams of convex lens. The first diagram is when the object is at infinity, the parallel rays coming from the object converge at a point, and that point is called focus. So if the object is at infinity, the convex lens will form the image on focus, but on the other hand of the lens. If it is beyond 2f1, it will form the image on the other hand side. It will be real and inverted, and it will be between 2f2 and 2f2. When it is on 2f1, image will be formed on 2f2 on the other hand of the convex lens. Size will be same. In the first two, size will be very diminished, the first one, and here it will be diminished. In the third, it will be same as the size of the object, but it will be real and inverted. When the object is kept in between 2f1 and f1, the image will be beyond 2f2 and will be the of larger size than the object. In fifth diagram E, you can see when you keep an object at focus, image will be at infinity. When you keep the object between the optical center and the focus, image will be at infinity, but this time it will be virtual and erect. Here it will be at infinity, but it will be real and inverted. So this sixth diagram can be better understood in this table. Position of the object is at infinity. Position of the image will be at focus f2. It will be highly diminished, point size, real and inverted. If the object is at 2f1 or beyond 2f1, the position of the image will be between f2 and 2f2. Relative size of the image will be diminished. It will be real and inverted. At 2f1, the object, the image will be formed at 2f2. It will be of the same size. It will be real and inverted. When the object is between f1 and 2f1, the position of the image will be beyond 2f2. It will be enlarged, real and inverted. When the object is kept at focus, the image will be at infinity. It will be large or highly enlarged, will be real and inverted. But if it is kept between the focus f1 and the optical center O, it will be on the same side of the lens as the object. It will be enlarged and virtual and erect. Just like we had seen in mirror, the concave mirror, 5 diagrams were having real and inverted image, and the sixth diagram was having virtual and erect. Now let's study about concave lens. In concave lens, the object is kept at two different places. If it is at infinity, the position of the image will be at focus. It will be highly diminished point size. It will be virtual and erect. If it is kept between infinity and the optical center, anywhere on the optical center, position of the image will be at focus f1, and between the focus f1 and the optical center, relative size of the image will be diminished, virtual and erect. These are the two diagrams that we have studied in that table. When the object is at infinity, image will be formed at focus. It will be virtual and erect. When it is kept between infinity and the optical center, in between any of the place, it will be still, virtual and erect. Sign convention for spherical lens. Sign convention for spherical lens. This is similar to the sign convention for spherical mirrors. But in mirrors, everything was on the left hand side. In lens, the image mostly will be on the right hand side. So the distance from the optical center to the image will be positive. It may be negative if the height is downward, that is, real and inverted image will have a negative height. The object will be on the left hand side of the lens, so it would be having negative distance and its height would be positive. The light rays would be incident from the left towards the right. Lens formula and magnification. We have a formula for spherical mirror. The same can be said for spherical lenses. This formula gives the relation between object distance, image distance and focal length. Here there is a subtraction sign instead of positive sign. 1 upon V minus 1 upon U is equal to 1 upon F, and this formula is considered as lens formula for all situations for any spherical lens. Magnification. Magnification produced by the lens, similar to that of the spherical mirror, is defined as ratio of the height of the image and the height of the object. So here also magnification is equal to height of the image to the height of the object. It can also be related to the object distance and the image distance. So V upon U is also the magnification in lenses. You have to note that in mirror it was considered minus V upon U, but in lens it is considered as V upon U only. Let's talk of another topic, power of a lens. The ability of a lens to converge or diverge light rays depends on its focal length. A convex lens of short focal length bends the light rays towards the large angle by focusing them closer to the optical center. Similarly, a concave lens of very short focal length can cause higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by the lens is expressed in the terms of its power. The power of a lens is defined as the reciprocal of its focal length. It is represented by power P. The power of the lens of the focal length f is given by P is equal to 1 upon f. The SI unit of power of a lens is dioptry. It is denoted by letter D. If f is expressed in meter, then power is expressed in dioptries. Thus 1 dioptry is a power of lens whose focal length is 1 meter. 1D is equal to 1 meter. 1 upon meter. One has to note that the power of the convex lens is positive and that of the concave lens is negative. This lens is actually the number prescribed by the opticians for correcting lenses.